Hello, everyone, and welcome to episode 12. Very excited to be working today with Andrea Davis and to welcome representatives of the U.S. Patent and Trademark Office. A couple of very quick housekeeping items, the typical things that we talk about, and I'll hand it over to Andrea for a few introductions. You'll notice on your control panel a couple of things there. First off, if you have a question, please put any and all questions into that section. I will be looking at those throughout the course of the conversation. And if it makes sense to interrupt and go ahead and put something in before we move on to a different topic, I'll go ahead and slow everybody down and ask those questions at that time. So please go ahead and put your questions in as soon as you come up with them. You'll also notice there are two handouts in the handout section. One of those is the slides that you'll be seeing, and another one is the actual paper that we're going to be talking about, the database that the Patent Office built and published on and is making available for people to use. And so you can also get that one as well. Finally, there is a survey, always a survey. Would really appreciate on your way out if you can take just a minute, even if you just answer the first question, which is to let the USPTO know if you'd like to know if you want to be on their mailing list, because of course they're interested in keeping in touch with everyone and sharing the news that they have from the office about machine learning and all the different initiatives that they have. And with that housekeeping out of the way, I'm going to turn this over to Andrea Davis.
Thank you, Tony. Welcome, everyone. We're delighted to have you here. There have been numerous guests in the ML4Patents webinar series, but I believe this is the first time representatives from the USPTO or any patent office are joining us, so we're very excited. I'm going to introduce you to our guests. Nicholas Perolero is a senior research economist in the Office of the Chief Economist at the USPTO. He's focusing on evidence-based policymaking with research in the economics of innovation. His research has appeared in peer-reviewed academic journals like Research Policy and has informed discussions in the US Senate and House of Representatives, and received professional academic awards, including the Department of Commerce Gold Medal for Scientific Engineering Achievement. Alexander Gitze is a data scientist with ADDX Corporation, conducting data-driven research in IP for the USPTO Office of the Chief Economist. His prior experience includes patent examination in aerospace technologies, and prior to the USPTO, Alex was involved in engineering, acquisition, and space operations while serving in the US Air Force. And of course, we all know our host, Tony Trippi, a foundational figure in the patent analysis space, coining the term patent informatics. Tony is currently with Owens Corning, as well as an adjunct professor of IP management and markets at Illinois Institute of Technology, teaching a course, of course, on patent analysis and landscapes for strategic decision-making. Tony has been named one of the top 300 IP strategists by IM Magazine, has written the guidelines for the preparation of patent landscape reports for WIPO, and we all know him as the developer of ML4Patents.com, the resource for the use of machine learning and artificial intelligence in the field of IP. Lastly, my name is Andrea Davis, and I've recently celebrated 5 years as the director of Botkin IP, a patent searching consulting firm I founded. I have been working in this fun industry for over 23 years, mainly in medical and mechanical technologies. I'm co-founder of the Patent Olympiad, and I love to stay involved in various patent information communities to spread the word about the value of patent information and the people that are part of this profession. So with no further ado, I'd like to invite our guests to start their presentation.
All right, thank you, Andrea. All right, great. Yeah, so our discussion today is on a project, the title Identifying AI Invention. Again, yeah, so my name is Nick Perolero. I'm in the Chief Economist Office at the USPTO. And I have my colleague Alex Gitze here too. He's a data scientist in the same office. And just kind of a quick background of the type of work that we do. So we are a group of economists and data scientists, and we focus on really kind of policy research. And I'm going to present one thing here today. It's of course a very big big topic, IP economics research. We do all kinds of things looking at diversifying the innovation ecosystem. We look at patent quality, litigation. I mean, it's really a wide variety of things. But today I'm going to focus on, one strand of work that we have that looks at invention in artificial intelligence. And this is kind of, where we've done a lot of machine learning, I guess, in the last couple of years, and how it kind of most directly fits in with the topic of this webinar series. So just kind of a quick overview, right? So I think most of the people here are probably, fully aware that artificial intelligence, innovation, and invention has grown quite rapidly in the last 10 or 15 years. I mean, it's a big field. It has a long history, but we've seen kind of, really rapid advance in the last, decade or two, I guess. And this has drawn sort of considerable interest from policymakers. And I think the really tough part is in trying to understand, what is the impact of AI on the economy is that, we don't have a lot of really good data on it. We don't have data really on which firms or which companies are adopting artificial intelligence. We have some information now that I'm going to present you today about, which companies, I guess, are inventing an AI, at least in terms of patents. But we sort of saw this and we said, okay, well, what can we do to help the situation? And I think the first thing is to really focus in on identifying which inventions, which patented inventions and patent applications contain AI. So, we released the data set. It classifies, which of several different AI technology components I'll talk about in a minute, which of these 13.2 million patent documents, pre-grant publications and patents contain, these sort of aspects of AI. Now, I think it's really hard, right? I mean, whenever you have a sort of patent landscaping exercise, you want to clearly define what you're looking at. And some things might be easier to define than others. Artificial intelligence, I think if all of us in this online room were to sit down and try to hash out what we mean by AI, I think it would be quite difficult. At least that was our experience. We had a kind of a big group within the USPTO, people from the patents business unit and the OCIO. We were trying to define what AI is. And we sort of, ended up with, I hope, with sort of a practical definition, right? So when we say AI, we mean that it is sort of, one of these 8, we call them, AI component technologies, speech, knowledge processing, AI hardware. If you're looking at, written language, natural language processing, vision systems, and of course, machine learning. That's the primary topic of this webinar. What do you have there? You have a system that's sort of, if it's supervised, it's learning from labeled examples, how to distinguish things and that kind of stuff. But this is our definition, and the approach that we built, classifies patent documents along each one of these components, right? And we'll primarily talk about, you're either AI or not AI, but just kind of keep in mind that we have the data there. That's are you speech, are you not speech, and for each one of these technology components. So, so this is a project. It's about landscaping patent documents, and we're going to use machine learning and natural language processing to do that. I think a lot of people in this webinar, they probably know exactly what I mean when I say that kind of thing. But just to be kind of clear, we're sort of, we're building a system, right? It's a machine learning system, and what it does, it looks at a set of labeled examples. We're going to call these seed and anti-seed. So this is language from a paper that was published in literature by Abood and Feltenberger. They're people at Google. But by a seed set, we just mean that these are labeled patent documents that we know or we think that they are in the technology of interest, right? So we call them seed documents, or they're in the seed set. And then for the anti-seed, these are documents that you sort of know or you are pretty sure they're not in the technology of interest. And again, for us, we're looking at these AI component technologies. So are you speech, are you not speech? Are you NLP, are you not NLP? And then what you do is you build an algorithm, right, that learns from these two sets. It looks at them, right? It looks at the text, the abstract, it looks at the claims, it looks at the citations, and it sort of learns from these two sets how to distinguish these two groups, right? Because we don't have every document labeled. If we had every document already labeled, we wouldn't need the system. We have a small number of documents labeled, and we want to unleash it after it learns to distinguish them on the 13.2 million patent documents world of USPTO published documents. So that's kind of a high level, summary of what the system is, what it does. And then I think the really interesting part that I, get excited about is that we had a group of patent examiners, of course, that examine artificial intelligence patent applications. And we had these examiners evaluate, right, 800 patent documents, and they went through them and they read them and they said, okay, this is NLP, this is not NLP. They actually manually evaluated them. And we sort of, benchmark our system relative to their, to their skill in sort of evaluating this. So that's, a lot of what we'll talk about a little bit later, this manual validation. So
let me ask you a quick question, Nick.
Yeah.
And I imagine some of this you're going to get into in a little bit more detail. So just stop me if you're going to talk about something a little bit later. But I know I would love to see either a concordance or some means of incorporating these categories into the CPC. It just, when I first saw this paper come out, I thought to myself, you know what, this is actually a much more thorough job. Yeah, even if you go back a few slides, if we look again at all of the different aspects of AI that has been identified by the office, I thought this was a very good way of breaking it out. I thought it was very practical and certainly contained, like for instance, AI hardware. I had to do some work. Actually, I wrote a Forbes article on AI hardware, and it wasn't easy to identify those items that were AI hardware. There's a handful of CPC codes, like one specifically for machine learning, and then there's other computational methods in there in the G class that talk about some of the various different methods, but nothing that really hones in on these really nice, useful, practical categories. So it would be really great at some point, if it's not already in the works, to see about getting some of these more thoroughly incorporated into the CPC, so in the future it becomes a little bit easier to work with these.
Yeah, that's a really, really great comment. And actually, it really kind of segues into this next bit. And I personally can't go into enough detail that I think that this question deserves, but I can tell you a little bit about what's going on, and maybe Alex can chime in on the actual concordance that we used, right? So for each one of these, AI technology components, again, this is AI hardware, this is machine learning, et cetera, right? We had to develop a seed set. And the idea is that, you want to, for this method that I'll sort of describe in a second, you want to identify a set of true positives or patent documents to be true, or, they're actually in the technology of interest. You want to identify, this set that you're going to eventually feed into the system. So what we did was, we looked at these different classification systems, right? So you have CPC, IPC, USPC, and you have Derwent. And what my colleagues did, they're like, okay, well, we need a set of documents. We know that we can't get all of them, right, by using, these classification systems, but let's try to get a set of around 1,000, right, each one of these technology components. And so what they did was they said, okay, well, we think that you're going to be AI hardware and USPC for these codes. We think that you're going to be AI hardware and IPC if we sort of use this, IPC-based query, CPC, et cetera. And then what they did was they intersected them, all right? So by intersecting them, it kind of made us, well, at least we think that you're this technology, AI hardware, in all of these classification systems. And then we were, I'll show you the summary statistics, but we're trying to get about 1,000 documents within each category. I can't say more than that here because I wasn't the one that sort of wrote the queries, but we have them written up in the paper. You can see, so if you go to the back in the appendix, it'll show all of the queries that we wrote to identify the seed sets for each one of these components. And I'll see if Alex, do you have anything more to add about, for example, with AI hardware or with one of these other technology components, what they really kind of consisted of?
Yeah, so the appendix B inside the paper, the working paper that we have, shows where we started from. What are the queries? What are the CPC codes, the IPC and the USPC, along with some keywords as applicable in order to start with that seed set. And then once you put it into the model, however, the model then learned off of that and then went into different areas, different patent areas. So as you'll see later on in the presentation, the number of CPCs that may be associated with AI is increasing in time. So it's not like it is confined to a small group of CPCs. And again, that's depending on what your definition of artificial intelligence is. We took a rather broad view of what our artificial intelligence is, and so forth. So a one-to-one correspondence is difficult to do because AI starts to get into everywhere.
Yeah. Thanks, Alex.
Were there any differences between the 8 different categories? I know some of them go way back in time and other ones are newer technologies, and I would think that one model doesn't necessarily exactly fit all of them.
Yeah, exactly. Yeah, so we're going to end up running, each category has its own model. And eventually I'll show you some summary statistics where it kind of shows the growth of each component technology. So you can kind of see, you know, when does one start, when does it kind of taper off and that kind of thing. So that'll be a little bit later in the slide deck. Great. So, you know, this is sort of the start of the approach, right? So for each of these component technologies, we want to identify a set of documents that we think are in that technology. We call them the seed set. And then we're using this approach by these people at Google, Abud and Feltenberger. And what they do is they say, okay, well, from the set that you think is in the technology of interest, we're going to sort of expand away from that, right? We're going to expand away from it using citations, using, you know, family members, using CPCs in the sense that we want to sort of expand away and find technologies that are, you know, dissimilar from the seed set. So you do these sort of expansions, right? And then you end up far away. And then once you get far away enough, you randomly sample 15,000 patent documents to be the anti-seed set, right? The idea is that as you get really far away, you sort of expect these to be documents that you don't think are in the technology of interest. So they call it sort of semi-supervised because there's no labeling being done here. You're sort of, you know, you have a query that you use to find the documents you think are in the technology of interest. So you want to have you know, a very kind of nice query in the sense that you want to be very sure that it's identifying the right documents. And then what you do is you sort of expand away from that, and hopefully you get far enough away that you're identifying documents that aren't in that aren't anywhere in the technology of interest, right? So it's semi-supervised in that sense. You're not actually like, you know, randomly sampling documents or labeling documents, you know, with people at this stage. It's sort of, you know, semi-automated in that sense. So for each one of these, yeah, go ahead.
Apologies, have to ask, and everybody's heard me talk about this before, the continuum between apples and astronauts, and apples and fish, apples and oranges, and 2 different types of apples. Now, I know you can't say definitively how broad or how far on that continuum you got away with the anti-set, but do you have a sense, either one of you, Alex, Nick? I mean, are we really talking about apples and fish or apples and astronauts, do you think, in these particular cases?
Yeah, it's really apples and astronauts, right? You're getting so far away. And that is the primary weakness of this method, is that you are not finding documents that are on the boundary when you use the expansion. So it's good in the sense that it produces, you know, a seed set and an anti-seed set that are very different, and you're, you know, and I'll show that, you know, the approach is highly accurate, right? So if we're in the seed, you are definitely in the technology of interest. If you're in the anti-seed, you are definitely not in the technology of interest. But with that said, it's not very good at finding the boundary, right? So that for sure, that's a great point, and yeah, it's a weakness of this approach. So
yeah, I wouldn't call it a weakness. You know, as a matter of fact, I mean, you know, you want the model initially, especially when you're talking about 15 million, 11 million, you're talking about huge numbers. At a first pass, you'd like this to be more precise than not. And so, you know, getting it so that your confidence level in what it is that you're bringing back based on the model is going to be higher, because, you know, now, frankly, you might miss a few things, you know, so your recall might drop a little bit. But I think in this case, because of what we're talking about and the huge numbers, you'd want to maybe err on the side of higher precision. So I'd say that, it's just a feature of the model as opposed to,
Sure.
just the way that you did it on this first pass.
Yeah, absolutely. And I think, let's not talk about it right now, but we're sort of adapting this in ways to sort of, maybe maneuver around this a little bit. But it's a really good point. I mean, for sure. Yeah, they're definitely, quite far apart. Now, I don't want to spend too much time on this slide. We didn't do a lot of innovation here. We basically just added the claims into the approach that was developed by Abud and Feltenberger. But this is the architecture, right, of the top model that they described in that paper. And more or less what you do is you take the abstracts, you take the claims. We did add the claims. You sort of train a word-to-vec algorithm, right? And what does that do? It takes in the words and it, turns them into 300 length vectors, for example. And then you sort of stick these things into LSTM networks. You sort of thread that in, combine them with the backward citations that are one-hot encoded, right? So these are really massive vectors. They're just one-hot encoded vectors. You sort of combine those and you put them through another couple of neural network layers. And then you sort of, this is the system, right, that we're training for each of the AI component technologies. And if you want more information, we do provide more information in our paper, but you can also look back at the Abud and Feltenberger paper. That's really where this one came from. So these are the summary statistics, so you can get a sense of, when we executed this approach, what are the size of the training sets, for example. For the seed, these are the set of true positives. It's kind of on average 1,000, but it can be quite small. Like we had a hard time finding evolutionary computation. AI hardware, we identified a lot more documents than 1,000, 2,659. But still, these are, training sets that we're hitting about 1,000 documents, right? For the anti-seed, again, that was anchored at 15,000. We always randomly sampled 15,000 as was directed in the Abud and Feltenberger paper. But then it also shows the, the expansion, like as you're expanding, how is the set getting bigger? And then the remaining set, how many documents are in the remaining set? So it might give you a sense, Tony, of how far we're getting as we're sort of expanding out. Now, as a first check, right? So basically, we trained up one of these models for each of these AI component technologies, and the first thing we wanted to see was, well, how well do these models kind of discriminate with the predictions, right? So the idea is that, well, if you have a model that is either really, really sure you're not AI or really, really sure you are AI, then that might be doing a better job than if all of the predictions are at 50%, right? If you have a trained model and it predicts everything to be 50%, then the model's having a hard time telling you, what is AI and what is not AI, for each one of these component technologies. So this is just it's just a histogram, right, of the predictions, right, on all of the 13.2 million documents. So we've created our training data, we've trained our models, and then we predicted them on all of the sort of universe of USPTO patent documents. And what you see is for most of these categories, you see a lot of weight at no, at 0, right? I mean, most things are not AI hardware, for example. But then you see another, smaller weight at 1, meaning that, yeah, these documents are AI hardware or whatever the component is. Most of the time, we don't see a lot of weight at 50%. However, if you look at evolutionary computation, that's the second from the top on the left, you do see more weight at 50%, for these documents that were predicted to be evolutionary computation. Again, that's just above, you have a prediction above 50%. You don't see a spike at 1, so it's kind of like putting a lot of that weight all throughout and more so at 50%. So it sort of indicates that the model for evolutionary computation doesn't appear to be as good. It's having a hard time finding them. And it probably just reflects that we only had 82 documents in our evolutionary computation seed set. It could be that there are more, we just couldn't find them, but that's one key finding here, is that of all the component technologies, this indicates that perhaps the evolutionary computation is going to be less precise.
I just want to say that this is fantastic that you guys are putting out these graphs, because it gives transparency to these types of questions and how well does it work in each category, and where might we want to find a different model for a different subset.
Yeah, thanks, Andrea. Yeah, we're trying to really kind of put it all out there just so people, know what they're getting themselves into when they go and use the data, or definitely try to improve it. So the next bit is we can evaluate it, right? So this is the part that I get really excited about, is we're able to use patent examiners to evaluate the quality of this approach, right? And when we started this, we weren't sure about this expansion method. We weren't sure about our queries for the seed sets or the anti-seed sets. So what we did is we took kind of a stratified random sample. We just took 216 documents out of the seed, 216 documents randomly out of the anti-seed, and then everybody else, right, from the L1, L2, and the remaining, we took about 400 documents. We just took a simple random sample out of these different sets. And then what we did is we had, a set of patent examiners, and we had 2 patent examiners evaluate each document, right? And they went through and they said, okay, this is NLP, or this is vision, or this is all of these, component technologies. And then, the patent examiners can disagree, right? So we had directions that defined all of these things, but even with all of that, these are experts in the field, of course, they were still disagreeing, because there's always some, ambiguity here with what is AI, even within these technology components. So when people disagreed, we had a third adjudicating patent examiner, right? If they sided with this person, then that's what we ended up saying that it was. But the interesting part about that is, because we had 2 patent examiners for each document, you can basically use their disagreements to sort of evaluate how hard the problem is. All right, so this is a set of confusion matrices, and on these 3 different groups, seed, anti-seed, L1, L2, remaining, again, all this data is on the data that was labeled. And sort of the top, right, A or B, any AI, that just means that one of the examiners said that this was AI, and the bottom is one of the examiners said it's not AI. And when we're doing this analysis, this is all at the aggregated level. We didn't do all of this for each of the individual component technologies. I'll have a little bit more to say about that before, but it's just kind of a resource constraint when we evaluated here with the adjudication. We didn't do it at all of the individual components. We just said, okay, you're AI if you're at least AI in any one of these, NLP or whatever. Now, if you look at the kind of the far right, I mean, this is sort of the set that is the most interesting, because this is the set where it's not seed, it's not anti-seed, right? It's sort of like a random document that you pulled out of the patent corpus. And what we find is that, look, if a patent examiner said that it was AI, the adjudicator 40 times said that it was, but 75 times said that it wasn't, right? So it's pretty low precision, right? It results in about 35% precision, right? And sort of, what it indicates is that a lot of these documents had to be adjudicated, and this appears to be a hard problem, even for highly skilled patent examiners that look at this stuff every single day. Now, if you look at recall, okay, so there were 49 documents, right? It's the column. I know this is a lot of data, but there are 49 documents that were AI, and the patent examiners got them right 40 times out of the 49. So the recall was 81%, but they had a tendency to sort of, at least one of the 2 that were looking at it to say it was AI when it sort of turned out not to be. So you average that, you get the F1 score of about 50%. So I think really this indicates that this is a hard task. I mean, this is the first time that I've done this. Had people sort of evaluate this and look at disagreements and stuff. But I think AI appears to be a hard task. It may always be a hard task. It might be exclusive to this technology, but that's, I think, one key point, right, out of this exercise, is that this is hard even for humans. So this is just for the seed and anti-seed. I won't talk about this too much, but what it shows is that if you look at, we use the adjudications that, okay, there was 2 and then an adjudicator, is it AI or not? It just kind of shows that the approach to identify the seed set was very good. When you expand all the way out, you find the anti-seed, it's very good. You're not putting documents in the anti-seed that should have been, true positives in the seed. So in that sense, the expansion methodology appears to be good at, getting you 2 sets that you can train on that, are pretty pure, right? So if you're in the seed, you actually are in the technology. If you're in the anti-seed, you're actually not in the technology. So we did a comparison with other studies. They're just, two other ones that we sort of pulled out. One is Ian Coburn and Scott Stern. They had a book chapter where they looked at just some sort of trends in AI patent documents, for example. They had a very, very narrow approach to identifying AI. They had a few keywords. I think they had one USPC, but it was very, very narrow. And really what happened was, if you look at everything outside of the seed and anti-seed, our remaining set, I think there were 40 documents there that should have been AI, and this Coburn approach didn't identify any of them. So it's sort of, it was just very, very narrow. And again, narrow is okay, right? I mean, narrow is okay if that's what you're looking at. If you only care about supervised learning systems, I think it's one of their keywords, and that's okay, right? I mean, that's what you're looking for. But so the Coburn approach is sort of quite narrow. We also recreated the WIPO approach. They had a really nice and thorough landscape study that came out that I think 2019, and theirs was sort of a classification keyword-based approach. Out of the 40 documents that we identified as AI in this kind of remaining set with the patent examiners, they classified 4 of them as being AI. So it's quite low recall, 10% recall. For precision, they identified 6 as being AI, 4 of them were AI, so you get much higher precision. But this is narrow as well, right? And again, narrow is not bad, right? I mean, if you're really focused on true positives, that's okay, right? But I think the idea is that when you use the classifications and you use the keywords, you have to kind of ex ante know where the stuff is, and you may be overly limiting, right? In that sense, at least with these 2 approaches. Now, if you take our approach, right, this machine learning based approach based upon a Boot and Fellenberger, what happens is that you end up identifying more documents as AI, right? So this thing, you unleash this thing on all of the world of patent documents, you identify more as AI, right? So what happens is you end up getting higher recall, right? Because you find more that are AI, you end up getting lower precision, right? There's always this trade-off between precision and recall. And, so if you look at recall, for example, we identified 15 of the 40. And for precision, right, we, out of the 32, 37, 15 were actually AI. So if you average these two, right, we're getting an F1 close to 40%, right? Again, the humans were 50%. Our F1, we kind of averaged the precision and recall is about 40%. The WIPO approach is about 17.3%, and the Coburn is just 0, right? They didn't identify any AI in our remaining set. So, it's kind of this hierarchy, right? The bottom line is that with the examiners, this is a very, very hard problem. If you use the machine learning approach, at least this implementation that we used, you end up getting higher recall, you get lower precision, you average them out, right? It sort of tends to be higher than these other 2 approaches. But the bottom line is this is just, it appears to be a very, very hard problem. So I know it's a lot of information. All of these tables are in the paper, and I'm happy to answer questions later by email or whatever there. But this is one thing too that I really like. And Alex created this, and basically, he was like, okay, well, let's look at the the patent documents where the examiners agreed, where they disagreed. And they can agree in 2 ways. They can agree that it's AI, or they can agree that it's not AI, or they can disagree. And let's look at this across all of the component technologies. Okay, so we sort of go across all these components. And for example, right, if you look at like planning and control, if you look at the green bar is the patent examiners agreed that it was planning and control. And then what we're actually plotting here is like the box plot or the distribution of our predictions with the model. And the median is the X, right? So for planning and control, if the examiners agreed that it was planning and control, the green bar, the X is quite low, right? So the median indicates that our machine learning model was saying that, the median at least, right, was that these were not planning and control. So in some sense, we might be under predicting, right, planning and control with that, for example. Now, if you look at like knowledge processing, the bars right next to planning and control. If you look at the red, right, that's when the examiners agreed that it was not knowledge processing. The X, the median, is very, very high, meaning that the median of the predictions was quite high, so that we were saying that it was knowledge processing, right? So these are the two categories that kind of jump out here as, perhaps we have worse performance on planning and control and knowledge processing. Sometimes there's just not enough data, right, to sort of say either way. But those are the two that really kind of pop out of this analysis where it might be better or worse on these components. So I know that's a lot to take in, but again, the graph is in the paper, and you can kind of dissect it more there. Alex, anything you want to jump in and add before I summarize the evaluation?
No.
All right. Yeah. So just to kind of summarize, basically, if you look at the F1 score, right, the machine learning approach, appears to be slightly better, right, than the other two kind of keyword classification-based approaches. But the bottom line is this is a hard problem. So even the F1 for the humans was only 50%. Our F1 was about 40%. So this is just a very hard problem. And I don't know, I'm interested in what people think. If it's just AI that, this is hard because it's hard to define AI, or if this is something that's just pervasive in the landscaping area. And if you look at, across the component technologies, we have different kind of indications of how well the model does across the component technologies. Again, evolutionary computation, I think our training data, the true positive set was just too small, right? Again, we had that buildup of prediction probabilities close to 50%. That doesn't appear to be as good. And there also might be something with planning, control, and knowledge processing, with the graph that either over predicting or under predicting based upon the graph that I just showed you. So let me just kind of quickly go through this, and maybe there'll be some questions. But we took the data set and we released a report a couple of years ago called Inventing AI. It really just looked at kind of the diffusion of artificial intelligence invention right across technologies, across patenting firms, and all this kind of stuff. Now, this is just a graph that shows public AI patent applications by the date that they were first published. It's usually a PG Pub date, pre-grant publication date, but it could be a patent date, for example. And the green is the number of patent applications each year. So, basically this is just growing over time. You have this sharp increase during AIPA that's just because, we had more patent documents that were published with pre-grant publications. So that's why you see that sharp increase there. But I think the really striking thing is that, we're getting a very large share, all right? A very large share of patent applications that contain some aspect of AI. Now, this is a lot more than machine learning, right? This is like planning and control and knowledge processing, right? Expert systems, vision, all of these aspects, and you're in here if you're AI in any of these component technologies. So perhaps with that broad definition, it's not so surprising. But these are the levels and the shares, that we're getting with this approach. And then I think, Andrea, you asked earlier, kind of, how does this kind of show up? What are the trends that we see within each of the AI component technologies? And we just basically broke it down. What are the public patent applications by each of these component technologies? And planning, control, knowledge processing, with the way that we had things defined and developed, those are quite large. They are driving the large share that we see in overall patent applications that contain some aspect of AI. We've seen a really large increase in machine learning right in the last 5 years. That's that kind of maroon or dark red line. Vision also had a pretty sharp increase in the last couple of years. So this data that I'm showing you here, this is updated through 2020. The report that we released only went through 2018, so you're getting a couple more years here of data. But it just kind of breaks it out by each of these components, and you can kind of see where the overall rate is being driven from, but also kind of looking at what's happening with each one of these aspects of AI. Now, I think this is really interesting, right? So here we start looking at, well, what is the diffusion of AI across technologies? And we looked at CPC subclasses. And we said, okay, do you contain at least 2 patent documents in, one of these component technologies, right? Then we looked at the share, right? So the dark green is what are the share of CPC subclasses that contain at least 2 patent documents in any aspect of AI? right? The vision line is you contain, vision patent documents, right? And you see this sort of steady increase, right, over time. Since 1976, that's when we started looking at, we have the data, I guess, on the text on patents. And you see this kind of, steady increase over time. But it just kind of shows that, we're finding AI inventions, right, all throughout technologies, and it's sort of continually increasing over time. It makes it hard. I mean, Tony said that it's hard to sort of identify the classifications, right, that contain AI hardware, for example, or these other aspects. This is just showing perhaps why it's hard, right, because we're seeing this stuff all throughout technology. And then I have two graphs here. I'm just going to kind of flip back and forth in these so you can kind of see, where in the United States, this is at the county, are we seeing these AI patent documents? Again, this is all of AI, all of these different component technologies. This is 76 through 2000, and this is 2001 and 2020. So you see the usual suspects here. You see like, Boston and San Francisco and, places near Austin and that kind of thing. But it just kind of shows you can go back to the report. We talk a little bit more about it, but where we're seeing artificial intelligence as it kind of diffuses across the country, I guess, geographically here. So just, let me just kind of quickly describe that. We have 20 minutes left. We can talk about questions, or I can keep talking, or, whatever we want to do. But, we're seeing a diffusion of AI broadly, right? We're seeing a lot more, larger volume. We are seeing diffusion across technologies. We're seeing diffusion across the United States. We're seeing a large share of assignees, right, that have at least one patent application in AI. I don't know what the numbers are off the top of my head. You can go back and look at the report. But again, this is growing over time. Companies are increasingly adopting artificial intelligence. So, the bottom line is that we're trying to make this as transparent as possible. We release the data set. We want people to look at the data set, use the data set in empirical work, improve the data set. The idea is that, we hope by releasing it, people will sort of do all of these things, and we'll kind of, improve our understanding of AI patenting, AI invention, and all of these things that we're interested in. So more information is available here. There's a published article. Tony provided the working paper of the article in the invite. It's the same as the published article. It just doesn't have the fancy layout. The report that I'm talking about was, you can get on our website. You can also get here, that shows the diffusion. And then just information about the data set. We released all the predictions. It's like 13.2 million patent documents. It's all of these, it's 70% machine learning, 40% planning and control. It goes through all of those probabilities for each of the patent documents. Then we also provide information on the training data. So were you a seed, were you an anti-seed, or maybe you were in one of these, expansions, L1, L2, etc. So all that's up there on our website that people can kind of, go up there and take a look. And I think that's all I have. So interested to hear what you all have to say. And thanks again.
Thank you, Nicholas. That was really, really exciting. And we're data geeks, so we love the numbers. I don't think we can ever get too much. We actually really appreciate all the work that you, Alex, and the team have put into making it so transparent. And in addition to that, taking these other studies and comparing the numbers so that we can really see the differences. So that's truly appreciated. With all these new filings, and it seems like there's probably millions of documents added since 2020. Are there any plans on keeping the AIPD sort of updated for the coming years?
Yeah, that's a really great question. So we are in the process of doing this. We're working with, we have a artificial intelligence, we call them Edison scholars, and they're basically, people that kind of work in the field or academics. They sort of come in to the USPTO and they sort of, help us with different projects and things. So we're working with Mark Finlayson. He's at Florida International University. He's a professor in natural language processing. But yeah, so we are working to update this data set. And I think, what Tony asked us about earlier, we're trying to build a system that helps us, identify and then manually classify documents that are close to the boundary. So I think the idea is to use this Boden-Feltenberger expansion approach that gets the seed and the anti-seed, but then augment that with, you know, manual labels, right? That are sort of found, you know, that are close to the boundary, and you can kind of retrain the system and, you know, find more documents that are by the boundary. And the idea is by manually labeling documents that the system predicts are like 50%, you're trying to help it improve in the places where it's most uncertain. So that's kind of coming, you know, we are working on that currently. There's also some algorithmic development that's going on, but the hope is to sort of, you know, improve the quality of the system and then release the data set, you know, sometime next spring. So that would be 2 years since we released it last time. But yeah, hopefully more to come on that.
That's great.
So we've got a few more questions from the participants, two in particular that I'll go ahead. I've got one myself also. So one of the people listening mentioned that a number of these categories are machine learning in and of themselves. I mean, like natural language processing. Natural language processing is a machine learning based method. So what is the distinction between the machine learning category here versus, say, natural language processing or vision?
Yeah, that's a really great question. So these categories, they overlap, and that's I think what the question is really kind of getting at the root of. Yeah, so they can definitely overlap, right? So you can be AI in more than one category. You know, I don't think that all of NLP is machine learning. You know, one way to look at it would be just be sort of like take words and assign part of speech tags, for example. So not all of NLP is machine learning, but I know a lot of the NLP uses machine learning. But you could find documents, yes, of course, that are both NLP. I mean, you could do that, right? You could take the predictions and say, okay, well, which ones are NLP and also machine learning, or which ones are ML and, you know, not NLP, and kind of, or which ones are NLP, maybe that's more interesting, which ones are NLP and not machine learning. And I think, you know, to really get at that, you could look at the seed, right, and say, okay, well, these are ones that we know are NLP, right, and find ones that are in the seed for NLP that are not in machine learning. I think that would be an interesting exercise, and it might kind of indicate, you know, a bit of the separation, but it is for sure that these are overlapping categories, and that is interesting for certain things, but it may be less interesting for other things. So I encourage people to kind of, you know, use it how they would like to use it.
That was actually my question about whether or not they were mutually exclusive. It did not seem as if they were. You've confirmed that they are not mutually exclusive, and yes, certainly there are going to be some that are going to have a high degree of overlap compared to others, which is not a bad thing, especially when you start looking at some of the trends that you looked at, because if you make something mutually exclusive, then you're by definition biasing some of the other trends. Because if the thing that's pointed at is, well, this is the priority, and you give a big selection a priority, well, then it starts to impact all the other trends, because that has such a big impact. Anyways, let me ask this second question, and the third question came in. This one's a little bit long, but I think it's a really well-stated question, and it provides some thoughts, some of which I think is actually, you know, right on. Claims in particular, they're not the easiest piece of language to work with. And so the question specifically, I'll read it exactly as they provided it. Is it possible that an ML struggles with all the ways that a technology can be defined, and hence a lower F1 score than hoped for, because patent applicants can be their own lexicographers? Wouldn't it be hard for AI approach to capture semantic meanings when alternative terminology is used? And again, my comment on that in particular is I'm never always a big fan of using claim language, just because of the absolute differences. The exact same concept being described by two different attorneys, and that claim language looks nothing alike. And so that just makes this that much harder. So do you have any comments or thoughts about that in particular?
Yeah. Let me pass it to Alex, and he can talk a lot more about that. Alex, are you still there?
Yes, you know, a very good, a very interesting question. So we added the claim language to the models, but we also still have the abstract in there. So the model you know, neural networks tend to be black boxes, so we don't know how much weight it put onto the specific claim language versus put onto the specific abstract language as well when it classified these patent documents. The other thing that I would add is we used Word2Vec in order to embed the word in order to embed the words, in order to translate the words into numbers that the computer can then understand. We did not use a bag of words approach, which is like kind of a one-hot encoding. And what Word2Vec gives you is kind of like a contextualization of it. So you might have a different word that is being used, but if the words around it are similar, then the Word2Vec is kind of going to say that, yeah, they're similar-ish type of concepts. At least that's what we're hoping for. Yes, claim language is definitely interesting because it's, you know, more legal than it is technical, or a combination of the two. So that's what it is.
Well, and that makes perfect sense. I mean, I don't want to give too much away, but I mean, when I do things like this, I tend to try and use a standardized source if I can find one. And so if there's means by which I can find language that's been standardized somehow, and I know there's some people, for instance, that run up some of their language up against a taxonomy, for instance, and so they're automatically taking words and standardizing a particular part of the vector such that you're losing some of that ambiguity. Anyhow, tough problem. That's the bottom line. And so, you know, again, you should be commended because it's a huge project with a lot of ramifications, and then you know, and really challenging topics. There's a lot of people in the data science world or the information retrieval world that just really thumb their nose at working with patent data because it's not like taking journal articles or other types of sources where the intention is to, as precisely as possible, portray information. And that cannot be said, generally speaking. I don't really quite believe the camp that people are actually trying to obscure things as much as people that say they do. But they're certainly not trying to make it crystal clear either. And so you've got that fine line that you got to walk with these. And you know, I should say at this point, because we're probably going to wrap up here in a few minutes, please everybody take the survey. And also we got a comment from somebody in one of the participants, thumbs up for the Patent Olympiad. So Andrea, you have a fan, and congratulations on the Olympiad. Somebody wanted to make sure that you heard that from them. Andrea, do you have any other questions that you'd like to ask Nick and Alex before we wrap up?
I can add one more thing too about the, you know, about how the language might change and how the language gets modified. And, you know, I think it's really something that we need to think deeply about, right? So like, if you train the Word2Vec model through data, you know, through 2018, and then you update the predictions through 2020, right, and that kind of thing, you know, the language changes, and then perhaps you're introducing, you know, biases and that kind of thing, right? So, you know, there's so many moving components, and I think it's really important to, you know, because I'm a user of the data, right? So I sort of want to know that something that I'm seeing that's changing, right, in the aggregate statistics or in some kind of like downstream regression analysis is really being driven by some phenomena and not some artifact of the data. So I think that's, you know, a part that I'm really starting to become more interested in is sort of, you know, we know that language changes, that people might, you know, I mean, they're trying to make things look as sort of new as possible. So it's sort of really important that we think really carefully about our training data and make sure that we're not artificially introducing biases and things by just sort of, you know, not training on the right information or that kind of stuff. So I know that's a super complicated area and it's a really important area, but I think that's something that I'm trying to think more about as we go forward.
Yeah, if I could make a suggestion, I don't know how easy this would be, but I've always thought that the best part of the patent was the summary of the invention. So the summary of the invention is not the background. It's not as complicated as the claims, generally more thoughtful than the abstract. So, you know, that section, that one little nugget in the middle of that document on the summary, and then you get the examples, and that gets convoluted and weird for a lot of different reasons. But that summary of the invention, you hope for some conciseness. Anyhow, but just a suggestion. I haven't even actually done any studies with it because it's not easy to get to. Most database systems don't have just that one small portion clipped out that you can use.
Yeah, I agree with you, Tony, that tends to be larger than the abstract, but more clear than the claim. So yeah, absolutely. One question I had, and sorry, I had some audio problems before, is whether, because we know the USPTO is using some AI tools in searching and classification, and whether your work has either been used by them in the AI technology or otherwise, and vice versa, if you've collaborated with those teams.
Yeah, so my colleagues across the organization are doing really, really great work in machine learning and artificial intelligence with classification and all sorts of things. We are sort of, separate in the sense that we're primarily a smaller research group of economists and data scientists. So they're not using this system. They have their own systems that they're sort of developing, and I think you can find more information about that on our website and through kind of public remarks. But yeah, I think our plan is to sort of, we're kind of a small shop, and we kind of jump on topics that are really, really interesting to the leadership in the USPTO, Department of Commerce, and kind of throughout. So that's where we started focusing on AI. Yeah, we're just kind of more specific in that sense. But yeah, it's a great question.
Awesome.
All right.
All right. Well, I think we're coming up on the hour here, right, Tony? So thank you very, very much. Don't forget to check out the handout section again. Really important, the grade, all those numbers are there in the handouts. And thank you, Tony, for making this webinar possible, and Nicholas and Alex for all your help with this.
And all everybody for attending today. We had, again, 90% of the people who started with us hung with us all the way through to the end, to the top of the hour. And so thank you, everybody. Enjoy the rest of the week, and we'll look forward to seeing everybody soon for episode 13. Take care now.
Bye.
Thank you.